Jack Payne, Grow Team Advisor with Co-op, and I'm at the Horseshoe Canyon Xtreme trial. And as I mentioned in some other videos, we talked about that we've got some extreme soil variability at this site, and it's something that we wanted to meet head on rather than run from it. And so behind me you can see a set of plots that we've got here. This is actually some of our Grown with Purpose trials, our fertility trials that we've got on hard red spring wheat. And the one thing that you notice right away when you look at this is we've got a gradient of slope here, and that's exactly what we wanted to look at, was to expose our treatments to different soil types. And one thing about this site, it's so unique that we have got a rapid change in soil properties within about 30 meters. So I wanted to use and capitalize on that variation to talk about how we can manage that from a fertility perspective. So when you look at the upper slope behind me, we soil sampled, we took a benchmark up there, and the results that we got, the organic matter level is 3%, the soil pH is 8 to 8.5. On the upper slope, there's about 20 pounds of available nitrogen, 48 pounds of phosphate, 560 pounds of potassium, and about 30 pounds of sulfur. Now that's what you would expect for a dark brown soil on an upper slope position like that. Quite typical. Now, where I am standing, we took cores from down here, we benchmarked them with GPS, and within 30 meters, here's the difference we've got. The organic matter at this spot where I'm standing is 5.4%. In other words, it's 2 to 2.5% difference. The pH is down to 7.6. As we would expect, as you move down slope, you've got more nutrients. So the nitrogen levels this spring were 40 pounds of available nitrate, 70 pounds of phosphate, 540 pounds of potassium, and about 65 pounds of sulfur. Now, our saline area, which we had looked at earlier today, if you were to look at the soil properties there, the organic matter level is down to 3.3%, and that would reflect the fact that there's very poor growing conditions down there. There's not much buildup of organic matter. The pH is quite high, it's about 8.1. And as you would expect, on the lower slope positions, we've got 24 pounds of nitrogen, 36 pounds of phosphorus, 350 pounds of potassium. Now, the one that really stands out is the sulfur. The sulfur levels in that lower slope position are 500 pounds per acre of sulfur. And somebody goes like, wow, that's a lot of sulfur. The thing you got to realize with saline areas, the majority of the salts that we have in our saline areas are calcium, magnesium, and potassium sulfate salts. Sulfate salts. So when they do the extraction, the sulfur separates from the potassium or separates from the calcium, and so that sulfur shows up as sulfate on your soil test, and so it skews the results. You may say, well, that's really good sulfur levels. It is, but it's really an unproductive area because we've got high salinity. So you have to use the results with a grain of salt, pardon the pun, when we're talking about saline areas. The good quality of high sulfur may be just a reflection of the high salts. So when we look at this site, what we've done is we've tried to adjust our fertility rates to take into account the differences that we've got with this landscape. So what we did is, rather than just talking about the soil qualities and properties, I thought what I would do is take my soil probe and actually pull some cores from the site. So these two cores are basically 30 meters apart, one from the upper slope and one from the lower slope. So I'm going to let you look at these and say, which one do you think comes from the upper slope? Well, one of the indicators of soil quality, of course, is organic matter. And usually the darker the color of the soil, the better the higher the organic matter levels are. So when you look at these two cores, you can actually see that there's a significant difference in the color of these soils. And so again, this one at the bottom would be from the upper slope position. You'll notice that there's a transition. You'll notice that there's a light brownish color here, and then it really starts to get quite gray, quite whitish in through this part. So again, what you've got is an AB, a very shallow AB horizon, which would be this seeding layer, and this is probably getting into the parent material. In fact, one of the ways that we differentiate our soils is we say the parent material is the material that the glaciers left when they retreated. And so the parent material is what was left 8 to 10, 12,000 years ago when the glaciers retreated. And typically parent material has very high levels of calcium in it. As the soils formed over the 10 to 12,000 years, the calcium actually was moved down. It leached down with water. And so typically what you'll find is your A horizon, B horizon typically will be low. in calcium levels, and then you get into higher levels in the lower portion of the profile where the calcium is accumulated. And so this is a way of measuring the depth of the profile and the quality of the soil. Now, if you look at the core that's above it, actually we look at this one and we don't see a lot of differentiation between the upper profile and the lower. And that would be a reflection again of soil formation over time, is that the soil on this foot of the slope at the bottom of the slope has accumulated much more organic matter over the years. It's higher moisture conditions in the lower slope position, and that calcium has been pushed right out of the profile. So when you look at the soil here, again, the soil test report was telling us that there was about 2.5% difference in organic matter. That is huge on a landscape, because soil organic matter, it takes decades, if not hundreds of years, to influence the levels of soil organic matter. And so this is absolutely huge. So to have that much variation within 30 meters, we wanted to capitalize on this as an education opportunity. So we're looking at these two cores, the two profiles, and one of the ways that soil people or pedologists investigate soils and look at them and try to determine where we're at is they use, where that parent material is they use a dilute solution of hydrochloric acid. So as I mentioned, we use hydrochloric acid to determine where the parent material is or where the concentration of calcium is. And so when we look at this core, we can actually see, if you look down here, it's very whitish. In fact, actually you can see some little white flecks right in here. That's probably calcium that's visible. But what we'll do is we'll take the acid, and what will happen is where we have high levels of calcium or where the parent material is, the acid will react with the carbonate in the soil and it'll fizz. All right, so we'll put a little drop here, and you can see that effervescence. It's really fizzing. Okay, so we've got some very high levels of calcium carbonate right there. So what we do is we work our way up from the bottom to the surface to see where the calcium transition is from, so where you've got parent material and where you've got topsoil. And so we'll try some there. You can see it's still fizzing, maybe not quite as much. You can see that there's some effervescence there and midway up. We'll go right about here where the transition is, and we can see quite a bit of fizzing and effervescence there. Now we'll go look at this section here. Oh, and you see that the fizzing is a little bit less. Do you notice that? So here's the transition. Quite a bit of fizzing there, and then in this area, not as much. So when we're looking at the depth of soil here in terms of topsoil, we're really kind of looking at that much, which would be about 3 inches. Okay, so we've got 3 inches of topsoil on the upper slope position. Now let's look at what the soil we've got 30 meters down slope. So remember the amount of fizzing we had here? There's absolutely none. Absolutely none. There. There. And so this is all topsoil. This is amazing. You've got a 1 foot profile of good topsoil 30 meters down slope from the upper slope material, which is, and even here at the top, you know what, there's still a slight bit of fizzing right in there on that top. So just giving you an indication of the soil variability that we've got at the site. Now that doesn't mean that you can't manage this type of soil. Now a couple of things that happen with these types of soils as well. The pH of this soil, as I mentioned, is about 8.5. Here it's about 7.6 or 7.5. The impact of pH on nutrients is quite substantial. When we have high pH soils that are high in calcium carbonate, typically what we see, there's less available phosphate, and there's also some micronutrients that become less available. And that's because the nutrients react with the calcium carbonate and become less available. So in these situations, we can run into some nutrient deficiencies that are caused by the high calcium levels. Now that doesn't mean that we can't grow productive crops on here, we just have to compensate for that. So for example, something like phosphate, it does not leach, it does not gas off, it does not break down, and so you can offset the tie-up of phosphate by putting on high rates of phosphate, and it's a numbers game. The more phosphate you put on, the less the more that is readily available and isn't tied up. And so you can build the bank account of phosphate on those areas of the field, and you'll never lose it like you will nitrogen. Nitrogen, of course, can leach, it can volatilize, and you can lose it over time. The other way of managing the phosphate is to use some of the newer products that are out there, for example, like Crystal Green. And we've got Crystal Green in the trial behind me. Crystal Green is a new product, a new fertilizer type that's out there. It has a unique method of release of the phosphate. It isn't as prone or isn't tied up as is 1152. And so it offers a great potential for, as another source of phosphate, to be able to treat some of these areas. As I mentioned, this is the difference that we've got just within 30 meters. It's substantial. It's a great opportunity to recognize the differences in your soil quality. And the more that you understand these differences, the better you can optimize your fertilizer application to extract better and higher yields out of your crops.